Welcome to Physics and Reality with Prof. Stuckey. I'm Emeritus Professor of Physics, Dr. Mark Stuckey, and in this video I'm going to resolve popular misconceptions about quantum superposition that people create by using Schrodinger's cat. While I'm at it, I will address a dispute between Kip Ingram and Mithuna Yoganathan that I found in Kip's Quora post about Mithuna's YouTube video on Schrodinger's cat. In order to keep this video relatively short, I'm going to omit some details. If you want to see those missing details, you can read our 2024 book with Oxford University Press, Einstein's Entanglement. I'm going to focus on the use of Schrodinger's cat as an example of the counterintuitive nature of quantum superposition. I'm not going to address any of the philosophical or historical nuances. But broadly speaking, Schrodinger and Einstein disagreed with Bohr and Heisenberg about the meaning of quantum superposition. To keep it simple, let's restrict ourselves to a system that is in a quantum superposition of two possible measurement outcomes, a quantum binary digit, or qubit for short. In that case, Bohr and Heisenberg believed that prior to measurement, the quantum system was in an indefinite combination of the two possible measurement outcomes, and that the measurement forced the quantum system into acquiring one of the two possible dispositions. Schrodinger and Einstein believed that the measurement merely revealed a pre-existing property of the quantum system. To make this point, Schrodinger supposed a cat was hidden in a box with a vial of poison that would be released, killing the cat, if triggered by a radioactive atomic decay. Suppose the probability of the radioactive decay in 1 hour is 50%. Then after 1 hour, he said the cat must be in a quantum superposition of 50% live and 50% dead. You can see Schrodinger's point, right? He's saying, come on guys, you don't really believe the cat is in an indefinite combination of live and dead, do you? Clearly the cat is either alive or dead, and our open the box measurement is merely revealing the true disposition of the cat with respect to this property. Mithuna made a great YouTube video about Schrodinger's cat that Kip responded to on Quora. The link to Kip's Quora post is there on the top, and the link to Mithuna's YouTube video there underneath. Here's what Kip had to say. At one point she tells us that the cat is really both alive and dead at the same time. No, the whole thing is not telling us the cat is alive and dead at the same time. In fact, the quantum state isn't telling us anything at all about the cat. The entire astonishing audacity of this whole thing just melts away when you accept quantum theory for what it actually is, an instrumental theory about our measurements. In the cat experiment, it's absolutely true that before you look inside the box, you have this quantum state. Psi equals in some combination there of cat alive and cat dead, right? But as noted above, this is not a statement about the physical cat. It's a statement about the measurement you have not yet made. That is, it's a statement about what you might possibly discover when you look inside the box. And in that sense, it's not astonishing at all. So let me point out here that Kip is conceding up front that Schrodinger's cat is in a quantum superposition, okay? Here's what Kip is responding to from Mithuna's video. Usually the interpretation of Schrodinger's cat is that you may or may not have murdered this cat. And because the box is closed and you don't know what happened, therefore both things must have happened. And they say it's like if you got a letter from your dream university accepting or rejecting you. Then until you open the letter, you don't know which, and therefore you're accepted and rejected at the same time. This is completely wrong. The case of this letter is just about ignorance. You don't know which happened, but one of them really did happen, and when you open the letter, you find out the truth. On the other hand, with Schrodinger's cat, there is no actual answer until you open the box, and that actually is a different circumstance. And it's even possible to prove that something different was happening inside of the box even while you weren't looking. So I'm actually going to do an experiment in this video to try to convince you of this fact. Schrodinger's cat really is alive and dead at the same time. Okay, so it's important to notice here that Mithuna is also conceding that Schrodinger's cat is in a quantum superposition. Okay, that's their starting point, starting assumption for both of their, both their claims. Mithuna uses the photon polarization qubit and the double slit qubit to support her claim. I'm going to use the double slit qubit. Mithuna doesn't use this terminology explicitly, but her examples are showing how everything comes down to the difference between pure states and mixed states, as we shall see. You don't have to worry about this technical language. My example will make everything clear. After I explain the nature of a qubit using the double slit experiment, I will point out its relevance to Mithuna's claim and Kip's response. I will also say who I think is right, Kip or Mithuna. But in doing this, we'll discover a bigger question for both Kip and Mithuna. Can you show me the experiment that really proves Schrodinger's cat is a qubit to begin with? Before I start with the double-slit qubit, let me contrast the qubit with the classical binary digit, or CBit. There are continuously infinite many different ways to measure a qubit, each producing one of two outcomes, the pure states. But there's only one way to measure a CBit. Here, an example. I have a box, and my measurement will be open the box. And I look inside. Aha! There's a ball. Or I open the box. In some trials, look inside, and it's empty. There is no ball. So those are my two pure states. Yes, there's a ball. No, there's not a ball in the box, right? And that's my... Now, there's only one measurement, open the box. But you could say, hey, Dr. Stuckey, what if I just shake it? Is that a different measurement? No, it's not a different experimental configuration. It's an equivalent measurement to opening the box, right? So, all right, let's use that as an example of my CBit. The CBit is what Mithuna depicted with her university letter example. The probability state P shown here is a distribution of outcomes for the one measurement that can be performed on the CBit, making it a mixed state. The pure states are 1, yes, the box contains a ball in my example, or accepted in Mithuna's example, right? And 2, like no, the box does not contain a ball, or rejected by the university. 1 and 2 are the actual outcomes of the measurement. For example, open the box or open the letter. The mixed state P does not represent the outcome of some other measurement, like the pure states 1 and 2. This is important. Now let's compare the CBit with the double-slit qubit. We start with the classical double-slit experiment, where two slits in a screen are being illuminated equally and in phase with monochromatic light. Again, don't worry about the technical terminology. Everything will be clear from the example, right? Okay, so different measurements are made by placing a detector at various distances downstream, from the two slits, okay? When the detector is placed immediately behind the slits, the outcome is the images of the slits. The picture there. Duh. I'm putting the screen right up against the slits. So, yes. When the detector is placed far from the slits compared to the slit separation, we see an interference pattern. This is Mithuna's figure here. She used a hair instead of two slits in a screen, but it's the same idea. You see there are two regions on the detector, red and black. Since we are illuminating the slits in phase, all of the light ends up in the red regions. That's where we get constructive interference when the slits are illuminated in phase. There. If one of the slits is 180 degrees out of phase with the other slit, then all of the light will end up in those black regions of the detector. That's where we get constructive interference when the slits are illuminated 180 degrees out of phase. So even if you don't know what it means to be in phase and out of phase, don't panic. You can still appreciate the conclusions that I'm going to show you here from the examples. Okay, now we're ready to make our double-slit qubit in the state 50% slit 1 plus 50% slit 2 in phase. All we need to do is reduce the intensity of the source until our detector starts displaying individual photon detection events. This figure depicts photons as particles, and it's not to be taken literally. Those balls are simply representing quanta responsible for the individual dots on the detector. This is the two-dimensional Hilbert space showing the basis vectors, measurement outcomes, for the two measurements we are performing on our qubit. Slit 1 and slit 2 are the outcomes of a which slit measurement. They're the pure states for that measurement. Since our qubit is in the state psi equals slit 1 plus slit 2 over root 2, the outcomes of a which slit measurement will be slit 1 with 50% probability and slit 2 with 50% probability. Slit 1 plus slit 2 over root 2 and slit 1 minus slit 2 over root 2 are the outcomes of an interference measurement. That's the pure states for the interference measurement. Notice that our state psi is an outcome of the interference measurement. Thus, if we do an interference measurement of our qubit in the state psi shown, the result will be psi itself with 100% probability. Now let's see what this means physically. When we place the detector immediately behind the slits, 50% of the photons land in the image region of slit 1 from the classical double-slit experiment. Psi becomes the slit 1 state. And the other 50% of the photons land in the image region of slit 2 from the classical double-slit experiment. That is, psi becomes the slit 2 state. This is a Witch slit measurement, and slit 1 and slit 2 are its pure state outcomes. When we place the detector far from the slits compared to the slit separation, all the photons land in the red regions of the detector and Mithuna's interference figure, image regions of constructive interference bands of the classical double slit experiment. That means psi doesn't change. So this measurement outcome literally represents 50% slit 1 plus 50% slit 2. Physically speaking, this just means the intensity of the light from slit 1 is equal to the intensity of the light from slit 2 everywhere along the detector in the classical counterpart, since the detector is very far away from the slits. This is what Mithuna meant by Schrodinger's cat really is alive and dead at the same time. This is our interference measurement, and psi itself is the pure state outcome in every trial. Here again are those red regions from Mithuna's figure. Here is a famous result of this interference measurement, where the photons are very gradually filling the image regions of the constructive interference band from the classical double slit experiment. Each and every dot is the measurement outcome, slit 1 plus slit 2 over root 2. So psi is the measurement outcome of the interference measurement with 100% probability. Mithuna might say, each photon really is associated with slit 1 and slit 2 at the same time. And Kip might counter, but this is not a Witch slit measurement. It's an interference measurement. 50% slit 1 plus 50% slit 2 simply means this measurement outcome totally randomizes the Witch slit information. That's the quantum information way of saying the Witch slit and interference measurements are complementary. So who's right? Let me summarize their claims. Mithuna. I'm actually going to do an experiment in this video to try and convince you that Schrodinger's cat really is alive and dead at the same time. And Kip's response is, no, the whole thing is not telling us the cat is alive and dead at the same time. In fact, the quantum state isn't telling us anything at all about the cat. Quantum theory is an instrumental theory about our measurements. All right, given that both Mithuna and Kip assume Schrodinger's cat is in a quantum superposition state, psi equals live plus dead over root 2, then there must be a measurement whose outcome will literally be 50% live cat plus 50% dead cat with 100% probability. Just like the interference measurement produces 50% slit 1 plus 50% slit 2 as its outcome with 100% probability. Therefore, this is not a mixed state representing our ignorance about whether the cat is alive or dead. Schrodinger's cat is in a pure state, which is the literal outcome of some measurement with 100% certainty. So, going into any measurement of this psi, this pure state, this quantum superposition, there is only one thing we know for sure, with probability 100%, and that is our cat is 50% alive and 50% dead. And I think this is what Mithuna means when she says Schrodinger's cat really is alive and dead at the same time. So, given their assumption that Schrodinger's cat really is a qubit, I would have to side with Mithuna. I would also say to Kip, the quantum reconstruction program has recently rendered quantum mechanics a principal theory like special relativity. So its status has risen above that of a mere instrumental theory. I'll provide links in the video description to videos, a book, and some refereed publications explaining that. But given what I showed you in this video, I want to challenge Kip and Mithuna to prove their fundamental assumption that Schrodinger's cat is a qubit. Here's the Hilbert space showing the measurement outcomes, pure states, of two complementary measurements where the state of their Schrodinger's cat qubit is an outcome of one of those measurements. The open-the-box measurement and its two pure state outcomes, live and dead, are all clear to me. But this could simply be a C-bit, like my ball-in-the-box example, or Mithuna's university decision letter example. In that case, our 50% live plus 50% dead is a mixed state, not a pure state, which means Schrodinger's cat is not in a quantum superposition. In order to convince me that Schrodinger's cat really is a qubit, i.e. it really is in a quantum superposition, justifying Mithuna's claim that it really is alive and dead at the same time, I need to know what measurement produces the outcome psi equals live plus dead over root 2 every time we apply it to Schrodinger's cat qubit. And what the hell does that outcome mean physically? It's clear in the case of the double slit qubit that our state psi equals slit 1 plus slit 2 over root 2 means every photon will land in the red regions of the detector in Mithuna's interference figure. That measurement and its outcome are physically clear to me. If you can't provide the measurement and its outcome complementary to the open-the-box measurement for Schrodinger's cat, I gotta believe Schrodinger's cat is a C-bit, not a qubit. And in that case, there is no basis for the claim Schrodinger's cat really is alive and dead at the same time. Again, if you want to see how quantum information theorists in the quantum reconstruction program have rendered quantum mechanics a principal theory like special relativity, read our 2024 book with Oxford University Press, Einstein's Entanglement, Bell Inequalities, Relativity, and the Qubit.